I've had several questions about this particular problem. You're given that a car, or given the position of a car is given by the equation. Now, we don't necessarily need to know why the car is moving at this type of an equation, but that this is just a mathematical representation of the motion of the car. You're asked to determine the instantaneous velocity around this point at 3.3 seconds. So this is what we're looking at. We want to go around this point at 3.3 seconds. And we want to do this over varying intervals. And the first interval that we're looking at is a change in time of 0.4 seconds. This one is a change in time of 0.2 seconds. And this one is at a change in time of 0.1 second. But the problem actually gives us our intervals that we're looking at. So I want to kind of go back and remind folks about what is exactly happening here. So let's look at a graph. So anytime I'm looking at a graph and I've got a curve, and this happens to be a position versus time graph, because remember what we're doing is we are putting back the mathematics to our description. And if I want to find the instantaneous velocity on this graph, I'm looking for that point. And our problem tells us that that point is 3.3 seconds. And basically what I'm doing is I am looking at the slope of the curve at that point. Now, if I'm moving into calculus, or if I'm moving into some other mathematics, we even talked about this in the book, and we actually discussed it a little bit in class, but I'm looking at the limit as my change in time is approaching to zero. So what I'm doing here is I'm looking at varying intervals, but I'm getting closer and closer to that particular point. So what's happening here is if I'm looking at my change in velocity, or I'm looking at my velocity, and we're looking at that instantaneous velocity, what I'm looking at really is my change in position over my change in time. So I'm looking at change in position over my change in time. So basically what this problem is asking you to do is find the position at time is equal to 3.5 seconds minus my position at time is equal to 3.1 seconds. And then I'm going to divide that divided by the interval, which was 0.4 seconds. And we're going to do that 3 times. And our book has actually asked us to do it to 3 decimal places. And there's a reason for that. So now let's come back and let's look at the problem. Basically, we were given in our problem the equation of motion that we're looking at. So this is our equation of motion. So let's write that out. So I've got my equation of motion. I've got x is equal to 6 meters per second times time plus 0.85 meters per second cubed times time cubed. First, let's look at our units. Time is in seconds, so that would be seconds will cancel out. I'm in meters. This is time cubed. I've got seconds cubed, and those will cancel out, and I have meters. So basically what we have is 6 times t plus 0.85 times t cubed. And so we were given our first interval, and that was t is equal to 3.10, and t was equal to 3.50 seconds. So if I solve for x, this is going to be 6 times 3.1 plus 0.85 t cubed, which is going to be my 3.1 cubed. And when I plug that into the calculator, I get a value that's 43.9223 meters. I'm going to do the same thing for this 3.5. And this gives me a value of 57.44375 meters. So now I'm just going to do my change in position divided by my change in time, and this is going to give me my 57.44375 minus 43.9223 divided by my 0.4 seconds, because that was my difference there. And we'll plug this into the calculator so that we know that we're getting this correct. So I'm going to clear all of that. 57.44375 minus 43.9223. That's going to give me a value. Divide that by 0.4. And that gives me a value of 33.804 seconds. So this is my first interval. I'm going to repeat that for my second interval. And so at t is equal to 3.20, I find that x is equal to 47.0528. At t is equal to 3.40, I get that this x is equal to 53.8084. I do the same thing, change in x over change in time, and I'm going to get my 53.8084 minus the 47.0528 divided by my 0.2 seconds at this point. We'll go ahead and plug that into the calculator. And I get a value. Oh, wait, that did not look right. Hang on, we'll do it again. And I get a value of 33.778. And this is meters per second. This is meters per second. So I've got two different values here. And what we see is very much like what happens as I get closer and closer on my curve, we see that there is a slight change in that instantaneous velocity based on where I'm looking at the curve. So what you're seeing here is it's trying to show you, the whole point of this problem is it's trying to show you that what's happening with that instantaneous velocity by looking at the tangent of this curve and getting closer and closer and closer to that actual point. Because what happens is we know that I cannot, if I'm looking at a velocity is a change in position over a change in time, and if time is equal to 0, we know that this is undefined. We can't divide by 0. And so what we're trying to do is make physical sense out of what is happening with that curve. So that's the point of this problem. And I think a lot of you make it a little too hard because what you're not realizing here is I just have a mathematical equation and I'm just evaluating it at 3 different time intervals. And what the whole point of this is to explain the motion that we're seeing on the curve.